Okay, we're moving into the last topic in this course. So we're going to implement lists. So again, we're going to create an interface for simple lists. We're going to implement a list in two different ways. And then hopefully when you see the implementation of the list, you'll understand why the list operations have the complexities that they do. All right, so you all know what a list is by now. It's just a sequence of elements, right? Every element has an index. So you have random, what's called random, well, it's not exactly true. You have what appears to be random access to the elements. We've been using the array list class a lot in this course. And so that's in a list that's backed, well, that's a list where the elements are stored in an array. We're also going to look at what's called a linked list, which we haven't used in the course. And in the linked list, that's where you use nodes to hold the elements in the list. Now, you would normally not do this on your own. So you normally wouldn't implement a list class on your own because the Java Standard Library already has the list classes for you. They're well tested, heavily used, well implemented. And so you would never ordinarily roll your own list data structure in Java. But it's useful to know how these lists are actually implemented so that you can, so that you really understand when and how you should use the different types of lists. The linked lists are important because many of you will end up taking the C course. And in the C course, you'll have to deal with linked data structures. Similarly, in your algorithms course and in your data structures course, you'll end up working with a lot of linked data structures. So Java's list interface is fairly big. We don't want to implement the entire interface. We just want to implement the quote-unquote important methods of the interface. Right, so methods like get and set, those are easy, so that's nice. Add, so add to the end of a list. Add, with this method here really should be called insert. So this inserts into the, somewhere in the list. Remove removes an element by index. And then we want people to be able to iterate over the elements of the list. So we're going to provide an iterator method as well. So there's our list interface, easy to create, right? So, oh wait, back up, what do we, okay, so our list interface, oh here it is. So our list interface is going to be called slist for a simple list. It's generic, right? So we have a generic type variable here. It has an iterator method, and that means we probably want to extend the iterable interface. By extending the iterable interface, we allow people to write for each loops on our class. We have so all of our methods are listed here, right? The isEmpty method is a default method because we can implement it in the interface. All we need is the method this.size, right? And we know that every list has a size method, so we can write the implementation in our interface. So now the classes that implement the interface don't have to redefine isEmpty. The rest of the methods, the way you implement them depends on the type of list that you're implementing, right? So in an array-based list, these methods in an array-based list look very different compared to these methods in a linked list. Okay, so in an array-based generic list, it's pretty similar to an array-based generic stack. The only complicating issue is this version of add and this version of, and this remove, and of course iterator. So when you add into the, or when you insert into the middle of the list, the way that it works in a list is that you have to move elements over to make room for the inserted element. When you remove an element from a list in an array-based list, you have to remove the element and then move elements back over one position in the array so that you don't have empty spots in the array. So these are inserting and removing is slightly more complicated compared to the stack and queue methods. Okay, so inserting into the array using an index, these pictures show you what happens. So I've got an array of, I have a list of size 9, right? 9 elements in the array. So anything in blue is an element in the array. Right? Notice that when we add the elements to the list, there's no gaps between the elements. Right? So we never have empty spaces in the array, except at the end of the array. Right? If I want to insert an element at this position, then what you need to do is you need to take all of the elements starting at the index where you want to insert and going to the end of the list. Right? I need to move these all over one position. because I need to make space for the new element that's going to go into index 4. Right, so I have to take those elements and I have to shift them over. And then I've got a free spot in the array where I can now add the element. That version of add is slightly unusual in that it allows, well, the Java standard library version allows you to add at the end of the list. So in other words, you can pass in an index that's 1 greater than the size of the list. Oh, sorry, that's equal to the size of the list. Sorry, it's equal to the size of the list. Right? Now, normally that index, so the index 10 is not normally valid for a list, right? So the only valid indexes in this list are 0 through 9. But the method treats the index that's equal to the size as indicating you want to add to the end of the list. Right? So this is a bit unusual, and it's going to complicate things slightly, as you'll see in a second. Now, to add at the end of the list, it's easy. You don't write your own method, right? You just call the add method that adds at the end of the list. Right? So if you detect that the caller is trying to insert at the end of the list, just call add, right? And away you go. Removing an element by index means you want to take that element out of the list, return it back to the caller, right? And you don't want to leave a blank spot in the list, right, in the array. So you have to move all the elements, all the red elements, right? I have to shuffle those over 1 position to the left, right? And you have to remember what the value of the removed, you have to remember what that value shown in yellow is so that we can return it back to the caller. Right? And so the list ends up looking like this, right? You just move all the elements over. Oh, sorry, we're not done yet. Okay, so those 2 pictures where we're inserting into the list and removing from the list, that should make it clear that inserting or removing an element in an array-based list has worst case complexity big O of n, right? Because you have to, you might have to remove up to, you might have to move up to n minus 1 elements, right? If you insert at the front of the list, you have to move all the elements in the list 1 position to the right. If you remove near the front of the list, you have to move up to n minus 1 elements to the left. And that ends up being in big O n. Right, so in general, you want to, if you can, you want to avoid removing or adding into or inserting into the middle of a list when using an array-based list. Right, of course, it's not always possible, but you have to be aware that they have complexity big O n. Our class sArrayList is the array-based list that implements the slist interface. Right? Now, it's going to look almost exactly like a stack or a queue, right? More like a stack. So we have an array of object to hold the elements, and then we have a field called size that indicates the number of elements in the list. Right? The index size is, oh, I don't have a picture here. The index size is the element that's 1 past the end of the list. We have a no argument constructor. It makes a new list, a new empty list. Right? So what do? Well, we initialize all the fields. Right? So for the array, we make a new array. And we have this default capacity field here. So this is just the starting capacity of the array. Right? This value is not critical. You can make it whatever you want. Right? Any non-zero value will work. You don't want to make it too big because you don't want to waste space. You don't want to make it too small because you want to avoid reallocating if you can. So you choose some intermediate value. Right? The size of the list is 0. Returning the size for an array-based list is easy. You just return this dot size. Whoops, sorry. Adding to the end of a list, it looks exactly like pushing an element onto a stack, right? Because you're treating the stack as though, because in a stack it looks a lot like a list anyway. So to add to the end of the list, right, you check, do I need to allocate space for the new element? Right, so is the size of the list equal to the capacity of the array? Right, if that's true, then you have to reallocate the array. Right, to reallocate and copy the array, you just use copy of. Once if you have to reallocate the array, you do so, and then you simply set the element at this dot size to the new element. right? And don't forget to increase the size of the list by 1. Right? So adding is exactly the same as push for a list, for a stack, sorry. Whoops, sorry. Add check index. All right, so most of the methods that operate on lists take in an index, right? And so it's, and in the standard library anyway, all of those methods validate the index. So you don't want to repeat yourself every time. So in this case, it makes a lot of sense to make a method that, whose only purpose is to validate an index. So we have a private method called check index. It throws an exception if that index is not valid for this list. Right? When's it not valid? Well, when the index is less than 0 or when it's greater than or equal to the size. Right? I've got an if statement here to handle the negative case and the positive case. And that's only so that you get back a more informative message. Okay, to get an element is easy, right? Check the index, right? If the index is valid, go into the array, right? Get the element at that index. Now that's a big O object because our array is an array of object. So cast the result to the element type and then return that value. Set's also easy. Set should change the element at that index to the new element, returning the previously stored element. So for the old, to get the current element, just call get. Right? Now the reason to call get is because get checks the index for us. Right? So I don't have to validate here separately. Get will do it for me. And then go ahead and overwrite the value sitting at the given index in the array. Right? And then return the old value. So set's also straightforward to implement. Right? You're basically getting and setting an element of an array. Notice that these are big O1. Right? All that we're doing here is validating an index, so that's just an if statement. And then either reading an array value or setting an array value. Right? So nothing here depends on the size of the list. This has these operations have constant time. Okay, add. So this is the insert method. Right? So I want to insert into the middle of the list somewhere. Well, possibly into the middle of the list. Right? Now remember, this version of add, you're allowed to pass in an index that's equal to the size of the list. Right? I can't validate that index using check index because it's going to throw an exception. Right? Our check index throws an exception if the index is equal to the size. So the first thing we do is check, is the index equal to the size? Right? If it is, then I want to add the element to the end of the list. So just call our add method. Right? Now, so don't, in other words, don't repeat yourself. Right? Don't rewrite all of this code here. Right? So just call add and then just return. Because that's it, you're done. Right? If the index is not equal to the size, then you validate the index. If the index is valid, right, now we have to do this shuffling of elements. Right? I have to move elements to the right to make room for the inserted element. Right? And now which elements do I want to move to the right? I want to move all the elements starting at index, right, and going to the end of the list. Right? Now if you start at index and move that element over one position, right, that ends up overwriting another element in the list that you don't want to overwrite. Right? It ends up overwriting the element at index +1. So what you want to do is you want to start at the end of the list and move things over one position. Right? So if I move the last element over one position, that frees up a space for the second last element. Right? Move the second last element over one position, that frees up a space for the third last element, and so on and so forth. So I'm going to start at the end of the list. Right? So I is going to be my index of the I is going to be the index of the element that I want to move. Right? Of the element that I want to move. So the last index in the list, the last element in the list has index size -1. Right? I want to move all the elements up to and including the element at index. Right? Now I'm counting down in this case, so I have to do I minus minus. Right? Now when I write this when I write the next statement, you have to be careful about the indexes. Right? So I want to move that element to the right. Right? So the position to the right is just I +1. Right? Now when you write this, when you write a statement like this in a loop where you're using an index, right, and the indexes are different, right, you have to make sure that both indexes are valid. right? So I know that my I index is valid, right? So index itself is valid. This size -1 is valid for a list, right, or for an array, right? So this one will never throw an exception, right? That's always valid, in other words. The question is that always valid, right? So is I plus 1 always valid for this list? I'll let you answer that question. Right. Once you've moved all the elements over to the right, go ahead and set the element at index to the new element, right? And then increase the size by 1. There is an error in this method somewhere, and I'll let you work out what it is. It's mostly correct. It's not quite correct. Okay, so for remove, I have to remove an element from a list, so that means I have to shuffle elements over one to the left. Right. I need to remember what is the current value stored at that index. Right. I also need to validate, is this index correct? Right? Is this index valid? So again, I'm just going to call get to do both. Right? Call get, that gets me the element currently stored in the list at this index, or throws an exception if the index is not valid. Right? At the end, I'm going to return the removed element. Right? So we're done with removed for now. I now want to move elements 1 to the left. Right? For this case, you can start from the left-hand side of the list, moving to the right. So in other words, I can count up in this case. I, again, is going to be the element that I'm moving, the index of the element that I'm moving. So I want to start moving elements at index +1, right? And I want to move them over 1 position to the left. So the index that I use here is I minus 1. Right? This will never throw an exception, right? So I know that I is a valid index. Is that true? Index +1. Oh, yes, sorry. So I is always less than the size, right? And it's never 0. It's never negative, right? Actually, it's never 0 either. So I know that I is always valid, right? Less than the size, never negative. So that's definitely valid, right? In fact, I know that I is never less than 1. Because index can't be less than 0, right? So I know that I minus 1 at least, is 0, right? So it's never negative either. And furthermore, I minus 1 is always less than the size of the list, so that's valid too, right? So that'll never throw. I've moved all the elements over 1 position to the left. That means I have a duplicate copy. I didn't really move them, right? I just assigned the array element. So that means I have a duplicate copy of the old last element sitting in the list. Right? So it sits at the very end of the list, is still a copy, it's still a copy of the reference of the last element in the list. So I'm going to null it out to make sure that if the list is empty, the garbage collector can now come along and get rid of that reference. Right? And then decrease the size of the list by 1. So in both add or insert and remove, you've got this inner loop where you have to move a bunch of elements around. Any questions about the inserting or removing from a list? Okay. The last method that we want to implement is this iterator method, right? So we want to provide an iterator for our list so that people can loop over the list, right? People can use for each loops. You also want to provide an iterator so that people can remove elements from the list as they're looping over the elements in the list. Now this means I have to return an object of type iterator. Right? So iterator is an interface, which means I need to create a class that implements the iterator interface. So our class is going to be called array iterator, and it's going to be a private nested class inside our array list class. So we have a private class called array iterator. It implements the iterator interface. Somewhere, okay, I don't actually tell you what it is. Somewhere I tell you what it is. Oh, I don't tell you what it is. Okay, so it's a nested class, right? It's actually an inner class, right? So this is an inner class, right? It's not static, right? So it's not a static nested class. So it's actually an inner class. Now remember what an inner class means, right? So an inner class object has a reference back to its outer class object. Right? So that means that an array iterator object has a reference to its list. Right? And that makes sense because you need a list for the iterator to iterate over. Right? So we get that reference automatically by making this an inner class. Right? That also means that the iterator has access to the fields of the list. Right? So our iterator can access the elements in the array, and it can access the size of the list, and it can access all the methods. Okay, so remember what an iterator is, right? So an iterator is an object that knows how to iterate over a collection of elements or a sequence of values. Right? We've implemented one, I think, so far. Right? We did that range class that lets us, basically, it was basically a counter. Right? So now we need an iterator that can iterate over an array-based list. Right? Iterators are important. So number one, they let people write for each loops, which is nice, right? For each element in our list, do something with the element. Right? But the iterators are also important because they're the only way that you can safely iterate over a collection and remove something from that collection while you're iterating over it. If you've read the list and set notebooks, you've seen an example of how to do this. Right? So the iterator interface has three methods that we need to implement in this class. Well, it has two that we have to implement. Right? It has next. We want to implement remove for our list. Right? So we want our iterator to be able to remove elements from the list as it's iterating over the elements. There is one more method. It's not important for us right now. Okay, so has next should return true if there is still some more elements in the sequence to visit. It returns false if there isn't, right? So if the iterator makes it to the end of the list, then has next should return false. Right? If the list has no elements in the list, then has next should return false. Right? Next returns the next element in the sequence and moves the iterator over one position. Remove removes the element that was last returned by next. So we'll come back to remove in a second. It's a default method in the interface, which means, so this is a way to create an optional method in an interface. Many of the standard library interfaces, when you look at the documentation for the methods, they'll say this method is optional. Right? So it's a bit strange to have an optional method. Right? So the way you implement an optional method is you create a default method and you throw an exception. Right? So in other words, if a class decides not to implement remove, then if someone uses an object of that type to call remove, they automatically get an exception. Right? So in other words, in the class that decides not to implement remove, you document the remove method as saying this throws an exception. Right? Okay, so the remove method removes the element that was most recently returned by next. Right? So the one that was most recently returned by next. So what that means is you have to call next before you can remove an element. Right? And you can only call remove once every time you call next. Right? So in other words, you can't say next and then remove. Right? You can only remove the most recently, the element that was most recently returned by next. Right? You get an exception if remove is called without first calling next, or if remove has already been called after the most recent call to next. Right? So if you try to call remove when you're technically not allowed, you get an exception. And so using an iterator is the only safe way to filter a collection. Right? So filtering means iterating over the elements, removing them as you go. So for example, if you want to remove all the negative elements from a list or set, you can do the following. So T is a reference to a list or a set. Right? You can create an iterator over that collection, right, by calling T's iterator method. Right? So all lists and sets have an iterator method. Right? So that gives you an iterator that returns integer values, right, because we have a list or set of integers. You want the loop to run as long as the iterator has some more elements to visit. Right? So we can use iter has next to control when the loop runs. Right? There's no update expression here because we're going to update the iterator inside the loop. Inside the loop, we call next. Right? So that gives us the element. That gives us the next element in the sequence. Right? When we start the loop, the iterator is at the beginning of the sequence. Right? So in other words, it hasn't looked at any elements yet. Right? First time through the loop, we call next, so that gives us the first element in the sequence. Right? Second time through the loop, you get the second element, and so on and so forth. Next returns the element, the next element. Right? So that's an integer in our case. If that value is less than 0, we're going to remove that element from the collection. And so the way you remove it is you call the iterator's remove method. Right? And so this will, at most, this calls remove once per iteration of the loop, which is exactly the way you should use remove. And so this loop here ends up removing all the negative elements from the list. Oh, sorry. Okay, so to implement an iterator, we kind of need a conceptual model of what an iterator actually is. Right, so in your text editor, right, any text editor that you use, you've got this flashing cursor. Right? You can imagine that that cursor is an iterator over the characters of your document. Right, so this iterator here is sitting between the Y and the I. Right? Now in our list, right, this iterator shown in red is also going, we can also conceptually think of it as sitting between elements. Right, so that iterator in red is sitting between the elements at index 7 and 8. Right? That element at index 7, we're going to call that, sorry, not the element. The index 7 we're going to call previous. The index 8 we're going to call next. Right? So if we call next on this iterator, we're going to return the element at index next. Right? The element that was most recently returned by next was the element at index previous. Right? So we know what the most recently returned element was, that's 13. We know what the next element's going to be, that's 6. Right? If you call next, the iterator moves over one position to the right. Right? So calling next advances the iterator one position. Right? We were between 7 and 8. We're now between 8 and 9. Right? When you get to the end of the list, right, so there's an iterator that's visited all the elements of the list. Right? The iterator sits between the last element in the list and whatever is after the list. Right? So hasNext should return false in this situation. Right? How do you know when you've reached this location? Right? Well, one way is that next is equal to the size of the list. Right? There's 15 elements in the list. Right? The next index is 15. Right? So we know that this iterator is at the end of the list. Right? If you try to call next with this iterator, you get an exception, right? Because there's no more elements to visit. When you make a new iterator, the iterator starts at the beginning of the list. Right? So it sits before the element at index 0. Right? Now we have to decide on what's the value of previous. So we're going to use previous equals -1 in this case. Right? So there is so whenever we have a value of previous that's negative, we know that there is no previous element. We're also going to use this to keep track of whether or not we can call remove. Okay, so here's the implementation of the class. Right? So we've got array iterator, which is a nested inner class, just an inner class. Right? So remember, this means that an array iterator object can get the size of the list and it can get the elements of the list. We have our field next. Right? So that's the index of the element returned by the next call to next. Right? And then we have an index previous. That's the index of the element returned by the most recent recall to next. Right? We're going to reset this to -1 if the element was removed using the remove method. When you create a new iterator, right, we start at the beginning of the list. So our next index is 0. Because that's going to be the first element in the list. Right? Previous is going to be -1 to indicate that we haven't called next yet. Okay, now remember our nested class, our inner class has access to the fields of the list. Right? So for hasNext, we want to know, right, is there another element in the list? Right? And the way we do that is we check next. Right? So if next is less than the size of the list, we know that there's still more elements in the list. right? When next is equal to the size of the list, we know that we've reached the end of the list, right? How do I get the size of the list, right? Well, you have to use this wacky notation again, right? So remember, if you want to get the field from the enclosing class, right, you use the name of the enclosing class, right? So that's sArrayList. Then you write .this. Then you write the name of the field, right? So that funny syntax there is the way that you get the field from an outer class, from within an inner class. Right. Now what about next? Okay, so next should throw an exception if there are no more elements in the sequence, right? So we use hasNext to check, are there any more elements in the sequence, right? If the answer is no, throw an exception. The exception that's specified by the Iterator interface is no such element exception, right? So that's one of the standard exceptions in the Java library. The next thing you want to do, right? So now I want to get the next element in the sequence and return it back to the caller. Right? So to get the next element in the sequence, I can call the get method if I want, right? Again, this is a method that lives in the outer class, so outer class name .this .get. Right? Syntax is awful, but that's what they decided to go with. You don't have to use the get method because you have access to the fields of the outer class, right? So you can just write sArrayList .this .arr, right? So I can go into the array directly and get the element manually, right? This is actually slightly more efficient because get performs a validation, right? And you know that the index is you know that the index this.next is valid, right? Otherwise, we would have thrown an exception up here. Right, so this is actually the better way to do it, the line that's commented out. Now, once you've got the element to return back to the caller, you're going to advance previous and next by 1. Right? So to advance next, I'm going to write next plus plus. But to advance previous, right, I'm going to write this previous equals this.next. Right? I'm not going to write this previous equals, or this previous plus plus. Right? And you'll see why in a second. At the end of the method, you return the element. So one more time, right? Check if there are still elements in the sequence, right? If not, throw an exception. Otherwise, get the next element in the sequence, right? Advance the iterator one position to the right, and then return the element. Okay, now how do you implement remove using this iterator? So here I've got my iterator sitting between the elements at indexes 8 and 9. Right? Remove is supposed to remove the element that was most recently returned by next. Right? So in other words, it's supposed to remove the 6. Right? Now after removing the 6, if you call next again, it should return the 10. Right? So it should, right? So you have to remember, so remove the 6, call next, we should go to the 10. Okay, so what happens when you remove the 6, right? So how do I remove the 6? Well, I can just call the remove method on the list, right? Because I know the index of the element I want to remove. Right? So the iterator can go in, ask the list to remove the element at index 8, right? I know what that index is because that's just previous, right? So what happens when you remove that element? So the 6 is going to disappear, right? So the 6 disappears. Whoops, sorry. The 6 goes away, and all of these elements are going to move over one position to the left. So the 6 goes away, and then all the elements move over one position to the left. Right? Now, notice where the iterator is. Right? The iterator is now between the 10 and the 4. Right? If I call next on this iterator, it's going to return the 4. It's supposed to return the 10. Right? So after removing the element, I have to back the iterator up one position. Right? So how do I back the iterator up to one position? Right? I take away 1 from next. Right? So we, decrease next. Right? So now the iterator is between the 13 and the 10. That's great. Right? The next points at the right element. Right? So now it's, if I call next again, it's going to return the 10. That's great. Right? I'm not allowed to call remove again. Right? Because I've already, we called remove once. You're only allowed to call it once every time you call next. Right? So I'm going to set previous to -1 in this case. Right? So we're going to make previous point all the way to the front of the list again to indicate that we can't call next again. Right? So we're going to invalidate previous, and that will be our indicator that we can't safely call remove again. Okay, so how do you implement this, right? So to implement remove, you first check the value of previous, right? Because someone might have called remove before calling remove again, right? So if previous is -1, we're not allowed to remove the element. That's according to the specification in the iterator interface, right? The method literally says you can't call remove more, you can only call remove once for every call to next. So if we've called remove already, or if there's no element to remove, right, you throw in a legal state exception. If we can call remove, then you just go ahead and call remove. Right? How do you call remove? Again, use the name of the enclosing class, .this.remove. Right? And that removes the element. Decrease next by 1. Right? And then set previous to -1. Right? Now, because we're setting previous to -1, this is why in next, right, you don't update previous by writing this previous ++. Right? Because if someone calls next, previous is -1. Right? If you add 1 to -1, you get 0. Right? Which might not be the correct element if you're somewhere in the middle of the list. Right? So if I'm here and I remove the 6, right, and back the iterator up, right, I want, when you call next again, I want previous to be equal to 8, right, the index 8. I don't want it to be equal to 0. Right? And so that's why when you update previous here, it's not this previous ++. Right? That's a very subtle implementation detail right there. It'd be very easy to advance the iterator by try to advance the iterator by adding 1 to previous and next. Right? If you do that, then you're going to get an error when you implement remove. Right? So this is an example of where it's really important to have a bunch of unit tests kicking around before you try to implement the method. Because it's very easy to make the mistake right here, and you won't realize there's a mistake here until you call remove, and then try calling next and then remove again. Right? So it's a very convoluted sequence of events that have to happen in order for you to realize that there's an error. And that completes the iterator class, which completes the list class. Right? So it's not tremendously difficult to implement one of these things, but there's a lot of little subtle things that you have to take care of. Right? So when you're removing from the middle of a list, you have to remember I have to shuffle elements over to the left. When you're inserting into the middle of the list, you have to remember you have to shuffle elements over to the right. And then when implementing the iterator, you have to pay very careful attention to how you update your fields, this.next and this.previous. Right? It's really not easy to implement this, to implement the iterator class correctly the first time. Right? Okay, singly linked lists. Oh, does anybody have any questions about the array-based lists? There's not much else you would want to add to the class. Well, I mean, there's a bunch of methods, extra methods in the standard library list interface, but most of the other extra ones are fairly easy to implement. Methods like equals are also easy to implement for a list, right? For an array-based list, right? If you want to know if 2 array-based lists are equal, just check if their arrays are equal, right? ToString is straightforward, right? Hash code, you just hash the array, right? So most of the remaining elements that we have, most of the remaining methods that we haven't talked about, pretty straightforward to implement. Okay, linked lists. So a linked list is like a it's closest to a queue that's implemented using linked nodes. Right? So in a linked list, you've got a sequence of nodes, right? Each node is connected to the next node in the sequence. In linked list, there's a traditional name for the first node, so that's called the head node. And there's a name for the last node, which is called the tail node. So in a singly linked list, each node has a link to the next node in the sequence, right? So that's exactly like how we implemented our queue. There's something called a doubly linked list. So in a doubly linked list, each node has a link to the next node in the sequence, and it has a link to the previous node in the sequence. So you can go backwards and forwards with a doubly linked list. Right? In a singly linked list, you can only move forward easily in the sequence. The Java standard library implementation of linked list is a doubly linked list. Right? We're going to do a singly linked list. So when you draw a singly linked list, it looks pretty much like a queue or a stack. Right? So there's a linked list of size 3, a singly linked list of size 3. Right? First node is called the head node, last node is called the tail node. Right? The tail node next link is always null. Right? If it's not, something's wrong with the tail node. Right? It's not actually the last node in the sequence. In the empty list, both the head and the tail node are null. Right? So you have no head node, you have no tail node. Just like the linked stack or the linked queue, the linked list is a recursive structure. Right? Every node in the linked list, you can think of that as being the head node of another list. Right? This makes implementing sublist for linked list very easy, by the way. We're not actually going to do that, though. Okay, so the element, so the first node here, that's the head of the linked list of size 4. Right? The second node, you can think of that as being the head node of a list of size 3. Right? The third node, you can think of that as being the head node of a list of size 2. Right? And the last node, you can think of being the head node of a list of size 1. Right? Now, because the structure is recursive, it's relatively easy to implement algorithms on linked lists that are also recursive. Right? So if you wanted to compute the size of a linked list, then all you have to do is count how many nodes are in the sequence. Right? How do you count? If you want to do it recursively, that's also easy to do. Right? So to recursively compute the size of a linked list, you make a little method that's recursive. Right? So rec size is a recursive method that computes the size of a linked list, starting at some specified head node. Right? So you start by calling the recursive method passing in the head node of the whole list. Right? The way this method is going to work is it's just going to add 1 every time that head node is not null. Right? And then it's going to add the size of the rest of the list. Right? So, so if the head node's not null, you've got one node, the head node. Right? And now you want to know, so the total size of the list is 1 plus the size of the rest of the list. Right? Where does the rest of the list start? Well, it's just head.next. Right? Because you can think of every node as being the head of a smaller list. Sorry, you can think of every node as being the head node of another list. Right? So if I go to the next node, that's the head node of the list of size n minus 1. Right? And I can find that size just by using the recursive size method. Right? And you keep on going until you get a head node that's null. Right? So in other words, when you get to the last node in the list and you follow that link to the next node, you get a null node. Right? The size of an empty list is 0. So you just return 0. So there's your base case, and there's your recursive call. And similarly, you can write pretty much, well, not all of them. You can write many of the linked list methods using recursion. Oh, sorry. I guess that's a good place to stop. And so we'll look at the rest of the implementation of a linked list in the next lecture. Wait, what's the next lecture? The next lecture is at 8:30, right? In the morning? Okay. So there's probably only one more lecture left in the course, which means that Friday is probably going to be no lecture. So I'll put a message on OnQ or tell you in the next lecture what's going to happen. Right? We should be able to complete the rest of the implementation of the linked list in the next lecture. Any questions? Cool.